Kia ora team and welcome to another online tutorial. Today we're going to be talking about the Level 1 Science 2018 Mechanics exam, specifically question 3. Let's get to it. So for question 3, Marama is snow skiing and uses the ski toe to get to the top of the slope. The ski toe pulls Marama up the slope to a height of 46.2 meters. The combined mass of Marama and her ski gear is 62 kilograms. A asks us to calculate the work done for Marama to reach the top of the slope. So as always, I'm going to write down any relevant equations. So it's a work question, so I'm going to write down the equation for work. Work equals force times distance. I'm going to check if I have those things. Okay, let's think about distance first. Yes, I've been given a distance. Force, no, I haven't. Okay. They've given me a mass, but I can use this mass to get a force. Okay. For that, I'm going to use the equation F equals mass times acceleration. Okay. So I'll do my calculation for force first, and then calculate work done. Force equals our mass, 62 kilograms, times our acceleration, which for at level 1 we say is 10 meters a second squared due to gravity. Okay. And that's going to give us 620 newtons, right? Now we have a force. We can use that in our original equation. We can calculate work. So we'll say that work equals our force, 620, times our distance traveled, 46.2 meters. And we're going to get our answer, 28,644 joules. Okay. Remembering to give our units, and work is the amount of energy transformed during an action, so it's joules. B states it takes 525 seconds for the toe to pull Marama to the top of the slope. Calculate the power needed to get Marama to the top. For this question, ignore friction. Okay. We always ignore friction unless they tell us to otherwise, or we're drawing a free body diagram, so we would have assumed that anyway. But first things first, we're going to write down the equations. So power equals work over time. Now I'm just going to have a quick check. They've given me a time, that's a tick, and work, I've got my previous calculation. So this is the only equation I need, relatively simple. Okay. We're going to just substitute those things in. Work done was 28,644 joules worth, okay? And we're going to divide by the time taken, 525 seconds, which is going to give us 54.6 watts. Remembering that a watt is just a joule per second. So you can give that if you want, but the actual unit is watt. Okay. Cool. Let's move on. C says that Jake has a mass of 75 kilograms and is doing a jump. Good for you, Jake. He has 3,200 joules of gravitational potential at the top of his height. Okay, so we're going to take in his mass as well as his potential at the top of his height, knowing that this is what they're going to ask us to transform into kinetic most likely. Calculate his downward vertical speed just before he lands, assuming energy is conserved. Okay. So this is definitely an EP equals EK question. Okay. Now, they've stated that EP equals 3,200 joules at the top of his height, right? And this is the same amount that's going to equal EK. So we've got the supplementary information in. Now we're going to make sure that we have any other relevant equation. We don't ever need to calculate EP, so we're not going to worry about this equation, but we do need EK. So I'm going to start off by writing in my EK equation, which is EK equals half mass times velocity squared. All right. With that, we're going to be able to calculate our velocity just like our question is asking. Now, they've said just before he lands, so we're going to assume that all of this has been transformed into this. Okay, so we've said that EP equals 3,230 joules, and that EP equals EK. So EK equals 3,200 joules. Okay, so we're going to say 3,200 equals, and we're going to substitute our stuff in. So half is very easy. Okay, so we're just going to put 0.5, and we're going to look for our mass. So our mass, which is 75 kilograms, so times 75, and that's going to be times our velocity squared. All right. Now, we're going to treat these as if they're in brackets, and we have 0.5 times 75 times velocity squared. Okay. Any times we want to get rid of a times, we're going to divide. All right, so we're going to divide both sides by 0.5 times 75. Okay, which will cancel out on this side, but give me 0.5 times 75 under 3,200 on this side. Okay, so I'm going to say 3,200 over 0.5 times 75 equals velocity squared. All right, now for us, we're looking at how to get rid of the square. The opposite of a square is a square root. If I square root one side, I have to square root the other. Okay, so I'm going to get V equals the square root of 3,200 over 0.5 times 75. Okay, and if I plug this into my calculator, I'll get V equals 9.24 meters per second. Okay. Now, if this confuses you, a good way to do it is knock 75 in half rather than keeping it full. When you divide 3,200 by this number, have that as a number, and you can have this number equals V squared, and then you can just square root this number if this confuses you. But there we go. We've got our velocity. V equals 9.24 meters per second. So, II is asking us to explain why Jake's actual speed when he lands is slower than calculated in part I. So, it's saying that his actual speed in real life was less than this. Okay. Let's talk about why. This is an efficiency question. Okay. Because we are not 100% efficient. But what does that mean? So, we're going to say due to friction, okay, some of Jake's energy is transformed into heat and sound. Okay, now heat being our primary one here, meaning there was less EK than calculated at the point of impact. Because EP was being turned into EK plus heat plus sound. Right. All we're saying is that it's not 100% efficiency. Not all the EP is actually getting turned into EK. Due to friction, some of the energy is being transformed. We don't say it's lost because we cannot lose or create energy. We can only transform it. Okay, and it's getting transformed into heat as our primary source, but also sound, right? Meaning there was less EK than calculated, right? And we can even finish it up with less EK equals lesser velocity, right? And we get a nice rounded off answer there. So 3D tells us Jake changes his wide skis. The skis measure 10 centimeters in width compared to his normal skis of 5 centimeters. Both sets of skis are the same length. Okay, So they're the same length, but his new skis are twice as wide. Okay. Now it asks us to explain why Jake does not sink into the snow as much when he uses his wide skis. Calculations are not required, but we're still going to write out our equation because it's going to help us talk about our answer. This is a pressure question. Now P equals force over area. Okay. Our pressure equals our force over our area. I'm also going to put in F equals M times A, right? Meaning force equals mass times acceleration. Now we're going to say, assuming, so we're making the assumption that the skis have a similar weight. The combined weight force is the same, or at least very similar. Okay, so we've said that our force applied is the same. So we've talked about this part of the equation. Now what's changed here is the area. The wide skis provide a larger contact area. What does this mean? Well, our pressure is force over area, meaning that a larger area, if force is the same, is going to result in a smaller pressure being exerted. Therefore, a smaller or lesser pressure is being exerted on the snow. So, less pressure exerted equals sinking in less. Okay. We said that pressure equals force over area. We've talked about force being constant, so force is the same for us in this particular one. The area has increased, meaning that pressure has gone down. Okay. So we described that saying that, hey, the force is the same. He puts the wide skis on. This provides a larger contact area. Therefore, less pressure is being exerted on the snow. Less pressure exerted equals sinking in less. Okay. So we have, for question 3, calculated work given a mass, making sure to turn it into weight force first. Okay. With our work, calculated power, we have then done an EK equals EP or EP equals EK question and done the transformation of energy and rearranged our equation to find velocity, right? We then talked about why this velocity isn't the real velocity observed in reality or real life, okay? And why this is. This is an efficiency question, and this is not a 100% efficient system. So we've said due to friction, some of the energy has been transformed into not EK, primarily heat and sound, meaning less EK, a lesser velocity. Okay. We've also looked at pressure and how changing the area, if you keep force the same, will change pressure or reduce the pressure exerted on the ground, meaning that you sink into things less. Primarily in this question, snow. Hope this helps, team. Hope it helps you to get out there and get into some mechanics and revise for your exam or test. All the best.